As we'll see later, knowing V and R for a given orbit, we can easily calculate the potential energy. We know that the potential energy of a charge Q at distance R is, let's try this again. Actually, I think I've got an error here. The potential energy of this thing is kQe squared over R, and that might not be reflected on the notes that you see. In any case, potential energy of the system is negative kQe squared over R. The electrostatic potential is what I had there, but that's potential due to the proton. We've got to multiply that by the charge of the electron in order to get the potential energy. Now, the kinetic energy, of course, is 1/2 mv squared, where m would be the mass of the electron and v its velocity. So that by substituting the expressions for r, the radius of the nth orbit, and v, the velocity of the nth orbit, we could obtain expressions for potential and kinetic energies. What we illustrate here is the n equals 2 orbit. The radius of this orbit would be 4 times the 0.529 angstroms. Remember, it's n squared times 0.529 angstroms. The velocity would be something that's not indicated here, but it would be approximately half of the 2 times 10 to the 6th meters per second, or about 1 times 10 to the 6th meters per second. Plugging this r in here and the expression for the velocity in here, we could obtain an expression for the total energy, the kinetic plus the potential energy. It turns out that when we do this, the potential energy will have twice the magnitude of the kinetic. So potential energy has the greater magnitude, but the potential energy is negative. It turns out then that when you add the potential and the kinetic, you get a negative energy that's equal in magnitude to half the potential or to the kinetic energy. And that's not really too hard to see. We'll see that in detail on the next set of video clips, next set of class notes. Now, if we go from n equals 2 out here, where the radius is 4 times the 0.529 angstroms, to n equals 1, where the radius is 0.529 angstroms, what happens to these energies? Well, the potential energy is negative here. It's even more negative here because R decreases, increasing the magnitude of this quantity. Since the quantity is negative, of course, then the potential energy will decrease as we go from here to here. The kinetic energy will increase as we go from here to here because the electron is going to be moving faster. It's going to have to move faster to get enough centripetal acceleration, or to require the kind of centripetal acceleration that we get from the proton at this proximity. So the potential energy decreases from one negative value to a larger negative value. The kinetic energy increases due to the increased velocity of the electron. But since the potential energy has the greater magnitude, the total energy is going to decrease. Now, when the total energy decreases, it's got to go somewhere. When the total energy of the electron decreases, something else has to pick up the energy and carry it away, or somehow keep it in the system even. But conservation of energy tells us that we can't have a decrease of energy here without a commensurate work being done or some increase in energy. Now, in this case, the increase in energy comes from a photon moving at velocity v. We use c for the velocity of a photon, or the velocity of light often, and that's 3 times 10 to the 8th meters per second. Now we have an energy decrease. Delta E is a decrease. Delta E is negative. The photon is going to carry the negative of that energy change, or negative delta E. Since delta E is negative, this will be a positive energy. The photon is going to carry this energy, negative delta E, away. And the negative delta E is actually going to be equal to the product of Planck's constant and the frequency of the light associated with photons of that energy. Okay? And this is the basic relationship, that a photon will carry an energy which is equal in magnitude to the product of Planck's constant and the frequency of the photon. Okay, so again, the electron falls from the n equals 2 to the n equals 1 orbital, there's an energy decrease, delta E. The photon carries away energy, negative delta E, a positive energy, and the photon will give rise to light having a frequency that's equal to h times f. A frequency such that h times f is equal to the energy of the photon. And that's the energy that we need to balance. And that takes care of our conservation of energy.